a quick review of two colligative properties, boiling point elevation and freezing point depression. If you look at the formulas associated with the two phenomenon, you see that they're very similar. We're going to calculate a change in temperature, and it's going to be determined by this factor I times a constant that depends on the solvent. Kb, B for boiling, is the boiling point elevation constant, and Kf is the constant associated with the freezing point depression. Note each of these depend on the solvent, and each of these equations involve m, the molality. Note that this is lowercase m, molality, or moles per kilogram solvent, not uppercase m, molarity. Let's take a moment to make sure we understand the physicality of what's happening here. Boiling point elevation, elevation raising. The boiling point of the solution is a bit higher than that of the pure solvent. The amount that the boiling point changes is delta Tb. So boiling point elevation, the boiling point of the solution, is a bit higher than the boiling point of the pure solvent. For freezing point depression, lowering, the freezing point of the solution is a little bit lower than the freezing point of the pure solvent, the difference being this delta Tf. Again, this lab is focused on the boiling point elevation, not the freezing point depression. Delta Tb is equal to I Kb times m. Now we've already discussed Kb and m, the molality. Let's spend a few minutes talking about I. I is the Van 't Hoff factor. It's related to the number of dissolved particles per solute unit. When we wish to determine the value of I, we first need to identify if the solute is covalent or ionic. If the solvent is covalent, every unit of the compound provides just one dissolved particle. For example, glucose is a covalent compound. We know that because it contains only nonmetal atoms. If we put glucose in water, it dissolves, and it goes from a solid form to an aqueous form. Each unit of solid glucose produces just one unit of aqueous particles. In ionic compounds, I is going to be greater than 1, and that's because ionic compounds dissociate into ions when they're dissolved in water. For example, if we had sodium chloride, a solid, we put it in water. Because it's an ionic compound, it's going to dissociate into its component ions. In this case, sodium chloride is going to go to sodium plus ions and chloride ions. Thus, each unit of sodium chloride, if dissolved and dissociated completely into ions, is going to produce 2 particles in solution. Calcium chloride, another soluble ionic compound. If it dissolves in water, it's going to produce ions in solution because another ionic compound, calcium chloride, when it dissolves in water, is going to dissociate into ions. In this case, we'll have a calcium 2 plus ion. Calcium's a 2A metal. It's going to form 2 plus ions. And this 2 indicates that we're going to have 2 chloride ions. So each unit here produces 1 plus 2, 3 particles in solution. And so for calcium chloride, complete dissociation, our I Van 't Hoff factor is going to be equal to 3.